Sam and Dizzy and Jesus. 8.8 is improper integrals. So the first thing we have to talk about is what the heck is an improper integral, and everything else that we've done so far has been proper. So what makes these improper? The definition of the definite integral requires that the interval from A to B be finite. Those are those brackets mean that the endpoints are included, so that interval is finite. And the fundamental theorem of calculus requires that a function be continuous on the interval from A to B. An improper integral just fails to meet one of those two conditions. So an improper integral is one for which one or both of the limits of integration are infinite. Either the lower limit's going to be infinity, the upper limit's going to be infinity, or both are going to be infinity. Or f has a finite number of infinite discontinuities. That's the most fun phrase today. A finite number of infinite discontinuities. That means f has a finite number of values for which the limit as x approaches c of f of x is infinity, or the limit as x approaches c of f of x is negative infinity. Now, I've seen that before. What does limit as x approaches c of f of x is infinity mean? What have we seen that as the definition of something? As x approaches this number, the function goes to either positive infinity or negative infinity. Try to picture that graph. There's some number. As x gets close to that number, the y's are either going to positive infinity or negative infinity. Did you figure it out, Aaron? Oh, I thought you had it. Major? It's a vertical asymptote. Why didn't they just say there's a vertical asymptote? I don't know. But there's a finite number of those numbers c where the y's are going to either infinity or negative infinity, so there's a finite number of vertical asymptotes. If one of those two conditions are met, then we're dealing with an improper integral rather than a proper integral. And the first thing we need to do is be able to recognize them. So on page 578, 1 through 8, just say decide whether the integral is improper and explain your reasoning. Remember, improper, one of two things happens. Either one or both of the limits is infinity, or there's a finite number of vertical asymptotes somewhere in the interval from A to B. So what about number 1? Proper or improper? And which? Improper. Improper because why? There's a vertical asymptote at 3/5, and 3/5 is on the interval between 0 and 1. So there's a finite number of infinite discontinuities, or a finite number of vertical asymptotes somewhere in that interval from 0 to 1. What about number 2, proper or improper? There is a vertical asymptote, but where is it? 0, which is not on the interval from 1 to 2, and so there's no vertical asymptotes on that interval, and neither limit is infinity, so that's a proper integral. What about number 3? Because why?
1 will make the denominator here.
All right, which means there's a vertical asymptote at 1, and it's one of the endpoints, but a vertical asymptote at one of the endpoints also makes that an improper integral. Good. And what about number 4? Proper? I see something that makes it improper. Not only did a vertical asymptote in the interval from A to B make it improper, but what else made it improper? One or both of the limits being infinity. That has a vertical asymptote at 0, which is not on the interval from 1 to infinity, but the fact that one of the limits is infinity makes that an improper integral. What about 5? Proper or improper? The exponential function doesn't have vertical asymptotes. It has a horizontal asymptote. The logarithmic function has vertical asymptotes. And the fact that neither of those limits is infinity or negative infinity means that's a proper integral. What about number 6? 6 and 7, easy because one or both of the limits is infinity. And then what about number 8? Where does cosecant have its vertical asymptotes? Cosecant 1 over sine, so it has its vertical asymptotes wherever sine is 0, and that is the left endpoint of that integral that we're trying to integrate. So that is an improper integral because one of its endpoints, or somewhere in there, the interval over which we're trying to integrate has a vertical asymptote, so it's improper. All right, first you got to recognize them, and then we have to figure out how to deal with them. Well, we deal with them by rewriting them in terms of limits. And this is not something that you have to memorize. It makes sense that if we're integrating from a to infinity, we can't use the inequality, or not inequality, we can't use the can't use the infinity symbol in the fundamental theorem of calculus. So when our upper limit is infinity, we're going to change that to the integral from a to b, and then just let b go to infinity. The limit as b approaches infinity of the integral from a to b of f of x dx. Or when our lower limit is negative infinity, again, we're going to change that to the definite integral from a to b, and then we're going to say, but we're taking the limit as a goes to negative infinity. And then if we have negative infinity to infinity as our interval over which we're integrating, we're going to have to split that into 2 definite integrals. And we can choose any number to make that break. We could always break it 0, or we could always break it 1. Sometimes with certain functions, some breaking points make more sense than other breaking points. So we'll look at one where we have to break an integral from negative infinity to infinity into 2, and then change each one of these into one of those. Yes, sir?
On number 1, how would you know what to set b as? Because it would give you a in the original problem.
Yes. Well, you don't set b as anything. You're taking the limit as b goes to infinity.
Okay.
You'll see that happen in just a minute. But we're going to be taking the limit as b goes to infinity. If those limits exist, the integral is said to converge. If any of those limits fail to exist, we say the integral diverges. And just a thing that will kind of blow your mind today, blows mine, maybe not yours. But when I looked at that figure 8.18 on page 567, it makes sense to me that if I'm integrating 1 over x from 1 to infinity, that area to the right is going to go on forever. The graph of y equals 1 over x keeps getting closer and closer to the x-axis forever. So that pink would go on forever, just getting shorter and shorter. When we find the limit using the definition that we were just given, we want to integrate from 1 to infinity. We find the limit as b goes to infinity of 1 to b, and then we integrate, and then we apply the fundamental theorem of calculus. We put b in the place of x and 0 in the place of x, and we evaluate that limit, that limits infinity. And that means that area is infinite. And that makes sense to me because it goes on forever to the right. It should be infinite, right? Just when you start feeling really good about, well, that makes sense, you see a problem that looks almost identical to it. Integrating e to the negative x from 0 to infinity. Well, y equals e to the negative x. That graph keeps getting closer and closer to the x-axis as well, but it never touches the x-axis. So technically that area goes on forever to the right, except for when you use the definition and you take the limit, that area is actually finite. That area is finite, that area is 1, even though the pink technically is going to go on forever. And the same thing here. This has a vertical asymptote, a horizontal asymptote at 0. The graph's going to keep getting shorter and shorter as we go forever to the right, but it is going to go forever to the right. Yet when we use the definition to change the integral from 0 to b as the integral from 0 to, that's a typo actually. That should be 0 to b. The limit as b goes to infinity. We integrate it. We apply the fundamental theorem of calculus. We take the limit. That integral converges as well. So example 1 looked pretty much like this, but it had an integral that diverges. Example 2, one of them has an area of 1, one of them has an area of pi over 2. So you can't just tell by looking at the picture whether or not the integral diverges. All right, let's look at these examples. And if you write very small like I do, you probably have enough room to do at least the first 2 on this page. If you write big, you may just want to recopy those on a different sheet of paper. But here are the steps we're going to use. We're going to rewrite the improper integral using this definition right here. And then we're going to find the indefinite integral using any integration technique that we've learned. I didn't run across any that I had to use a formula on. There were a couple, most of the problems in the homework were very straightforward. There are a couple I had to do integration by parts. One terrible one, I had to do integration by parts twice. So literally any integration technique that we've learned so far could be used in step 2. But once we find the indefinite integral, we apply the fundamental theorem of calculus. We plug in the upper limit b and the lower limit a and get that expression. And then finally, we take the limit of that expression that we got in step number 3. All right, let's see if we can do it. Number 1's an improper integral because the lower limit's negative infinity. When the lower limit's negative infinity, I can't just plug negative infinity into a by the fundamental theorem of calculus. So I have to take the limit as a goes to negative infinity of the definite integral from a to 0, 0 still my b, of e to the 3x dx. That's step 1. We rewrote that integral in terms of the definition for an improper integral. Step 2, we need to integrate that and find the indefinite integral for e to the 3x dx. What would that be? To integrate it, I'd have to have a 3 as part of the derivative. And to get a 3 as part of the derivative, I'd have to have a 1/3 out in front of the integral. And then if I did have a 3 here by putting a 1/3 here, what's the antiderivative of e to the 3x? Yeah. So that's step 2. I found the indefinite interval. Step 3 is evaluate that from A to 0 using the fundamental theorem of calculus.
You've got 1/3 on the outside of it to begin with because of the derivative of the e to the 3x.
Yeah, and actually, in the homework, I started in this step right here, going ahead and making that integrable by putting the 3 there and the 1/3 there in step 1.
So then when you integrate it, when you write e to the 3x,
No, the derivative, the antiderivative of e to the ugly, d ugly, is just e to the ugly. When you check that, when you take the derivative of this, you get the derivative of e to the 3x is e to the 3x times 3. That 3 times that 1/3 gave us back that coefficient of 1 that we started with. All right, step 3, evaluate that at 0 and subtract what you get when you evaluate that at A. Don't lose any part of the limit notation. We're going to take the limit as A approaches negative infinity of whatever expression we get when we put 1/3 in the place of, when we put 0 in the place of x. What will we get when we put 0 in the place of x? Yeah, just 1/3. Minus whatever we get when we put A in place of x. That would be 1/3 e to the 3a. And that's step 3. Finally, step 4 is find that limit. If A is going to negative infinity, what's e to the 3a going to? E to the negative infinity is going to 0 because that negative exponent throws the e down in the denominator. You have a numerator of 1 and a denominator that's getting infinitely big. So that's just 1/3 minus 0 is 1/3. And would we say that that integral converges or diverges? Since that limit exists, we would say that integral converges. And that would mean that even though e to the 3x has a horizontal asymptote and goes forever to the right, that area is finite. It's 1/3. Geometrically, I can't explain that. I can't explain how something that goes on forever is finite. sounds like an oxymoron there, but I can do the calculus and I can write the right answer. It just doesn't completely gel. Like one of Stephen Hawking's black holes or something. Can't explain it. Physics may prove it, but I can't explain it. Dizzy, yes.
Well, there's an infinite number of numbers between 0 and 1/3. So the area on that graph would be finite. But if there's a vertical asymptote and there's no limit, then the area would be limitless. It would be infinite.
Then how do you explain the difference between that figure 8.18? I mean, the same thing you're saying would be true there. We've got the limit from 1 to infinity. It goes forever to the right, and the integral diverges, which means the area is infinite. But in example 2, the graph also goes forever to the right. The area also goes forever to the right. How does that converge?
That would converge.
Right, and then what's the difference is what I'm asking. I mean, if you look at the picture, both pictures go forever to the right.
They don't go forever up the y-axis. At 8.19, it converges at 1. So the area underneath 1 will be finite.
No, that's not why, and I can tell you why. 8.19 and 8.20 do have x-intercepts of 1, y-intercept of 1. That's as far as they go. 8.18, we're not integrating all the way to 0. We're only integrating starting at 1. And starting at 1, that does have a left endpoint of the graph on the graph. We're not integrating all the way to the x-axis, or y-axis, but there's still a definite left starting point of where we're integrating. So that's not why this one's divergent. The other two are convergent, because this one we're not integrating all the way to the y-axis. So messes with my head, but I can do the math. I guess at this point in my life, that's what I'm going for. Just being able to try to do the math. All right, let's do it again with the integral from 1 to infinity of 4/4 through the x dx. Step 1, rewrite that with the definition, one of these. Rewrite it as a limit, and here it's our upper limit that's going to infinity. So we're going to write it as limit as b goes to infinity of the integral, not from 1 to infinity, but from 1 to b. And I'm going to go ahead and write that integrand in a way that will be most easy for me to integrate it. I write it as 4x to the negative 1/4 dx. That's step 1. Step 2, go ahead and find the indefinite integral. Add 1 to the exponent, that would give you 3/4. Divide by 3/4 is the same as multiplying by 4/3. And we get 16/3 x to the 3/4, which we need to evaluate from 1 to b. Don't lose any part of your limit notation. But we're ready to apply the fundamental theorem of calculus. Put b in place of x. And subtract what you get when you put 1 in place of x. And then evaluate the limit as b goes to infinity. What would that be as b gets bigger without bounds? Infinity minus 16/3 is pretty much still infinity. Subtracting 16/3 from infinity isn't going to make much difference. So we're going to put infinity, but that actually means the limit doesn't exist. We're just telling how it doesn't exist. And what does that mean about the integral? That it diverges. All right. These next two, I still managed to get them on my paper, but just to make them not so small that you're squinting trying to see it, I'm going to rework it here. By the definition, if our upper limit is infinity, then we want to rewrite that in terms of a limit. The limit as what? And technically, does it matter whether we use an A or a B or a C or a Z? No, and the solutions manual was inconsistent for just a split second. It bothered me that they had an A where I had a B, but that doesn't matter at all. As long as if your upper limit of integration is the one that is infinity, you make sure you integrate from some constant to whatever letter you choose. The limit as that letter goes to infinity. Same way if the lower limit is infinity, you're going to take the limit as some letter goes to negative infinity. Doesn't really matter what letter you use. So that's the limit as my upper limit, whatever I want to call it, goes to infinity of the integral from what to what? From 0 to whatever letter I've used here. And guess what it's going to take to integrate that? It's a product. It's a product. X times e to the, I prefer writing that as negative 1/3 x dx. All right, integration by parts. What do you want to let be u? By our acronym, the exponential part is the last letter of that acronym. It's the last thing we would let u be. So we're going to let u be the plain old x, and we're going to let, or that means du is dx. And if u is x, then dv has to be everything other than x. It has to be the e to the negative 1/3 x dx. And we integrate that to get v. We're going to integrate e to the negative 1/3 x. What do we have to have as part of the du? Yeah, we have to have negative 1/3 dx. And the only way we can legally get that negative 1/3 dx is if we put a negative 3 out front. So what does that mean v is? Yeah. All right, so I'm not going to lose my limit notation any part of the problem. We're taking the limit as b goes to infinity of whatever we get using integration by parts. Integration by parts starts out with uv. That would be negative 3x e to the negative 1/3 x minus the integral with the same limit, 0 to b, of v du. All right. I can go ahead and bring this negative 3 out in front of the integral, but again, to integrate that, and I'm going to put in a middle step that you may not need. The more I practice, the less I have to write this step. But I'm going to go ahead and bring the negative 3 out front and say negative times negative 3 is positive 3. But to integrate what's left, e to the negative 1/3 x, I have to have another negative 1/3 dx as part of the integrand. And the only way to get that is to put another negative 3 out front. Does that take integration by parts again? No, because I don't I no longer have a factor of x in there. The limit b goes to infinity, negative 3x e to the negative 1/3 x minus 9 times what? E to the negative 1/3 x. And that has to be evaluated from 0 to b. You can either simplify that expression you have in brackets before you can plug in the b and the 0 or not. Doesn't matter if you do or not. I usually did simplify it first. I factored a negative 3 out, and that left me an x plus 3. And I put the e to the 1/3 x in the denominator. Double check that. All right. All of that was step 2, find the indefinite integral. And so step 3 is evaluate that with the fundamental theorem of calculus. Put b in the place of both x's. And then subtract from that what you get when you put 0 in place of both x's. What's that second term turn out to be?
9.
And positive 9, right? So we just have the limit of this guy and then plus 9. What do we get if we try to do direct substitution with b as infinity right here? Which makes you think what? L'Hopital. Whenever we have infinity over infinity, that's one of the 2 forms that we can use L'Hopital's rule on. So really, I'm breaking this into 2 limits now. And I'm saying the limit of b goes to infinity of this guy and then limit of a constant is just the constant. So I'm through with the plus 9, I just need to keep up with it. If this, by direct substitution, gives me infinity over infinity, then what does L'Hopital's rule say that I can do? Take the derivative of the top and bottom. You can just notice this. You don't always have to write it down once you realize anytime you have a polynomial over e to the something, what is the numerator eventually going to differentiate to? 0 divided by huge is 0. Anytime you have a polynomial over e to a power, and that power is getting bigger and bigger and bigger, I'm just going to make myself this little note by L'Hopital's rule. I started to call it LaHop. I didn't say LaHop. L'Hopital's rule. That's 0 plus our 9 is 9.
Could you look at the step above that and tell that the denominator is getting bigger faster than the numerator?
Yeah, really you can, and that's why L'Hopital's rule is working. Even in this step, you can, or even before you ever heard of L'Hopital's rule, you could tell that that denominator is getting big a lot faster than that numerator. Sam, what are you thinking?
Instead of combining all of it together in one term, I have it separate, got 9 in one step.
And I noticed in the solutions manual that they do that a lot, and I wondered if there is a particular advantage to that. I was consistently doing what I did in Cal 1, expressed as a single fraction, factored as completely as possible. But in the solutions manual, they did consistently leave it in separate terms and evaluate those terms at b and 0. You can practice it both ways and see what you think, but I just did that out of habit. Yeah, get the same thing. All right. One more. Number 4. Can you already see what that indefinite interval is going to be when we get to it? Yeah, that's, if we bring the 3 out front, then that's just 1 over u squared plus 1, that's arc tangent. But here, both of our limits of integration are infinity, or negative infinity. So we need to split it. Is there a convenient splitting point for arc tangent of something that's easy to evaluate? Arc tangent of 0 is 0. The graph of arc tangent, we'll need this in a minute anyway. The graph of arc tangent kind of looks like x cubed. Arc tangent kind of looks like cube root of x, where it has the horizontal asymptotes, negative pi over 2 to pi over 2, and it kind of looks like this, approaching both of those horizontal asymptotes. So 0 seems like a good splitting point. Technically, we could use any splitting point. But 0 looks like a good splitting point because it's easy to evaluate arc tangent 0 if we need to. All right, so we're going to split this up into the integral from negative infinity to some point we've chosen to be a. And another integral from 0 to infinity and so we're just doing 2 baby limit problems similar to the ones that we've been doing. We've got to write this first improper integral as the limit as what? A goes to negative infinity. The integral from where to where? A to 0. And we'll write the second one as the limit as what? B goes to infinity of 0 to b. Again, it doesn't matter if you set yours up this way and you look in the solutions manual and they've used b for the first limit, a for the second limit. I don't know why they kept doing that when that's not how they wrote the definition, but it absolutely doesn't matter. All right, the limit as a goes to negative infinity of, what would that indefinite integral be? 3 arctangent x evaluated from a to 0 plus the limit as b goes to infinity of 3 arctangent x evaluated from 0 to b. That's Step 2, we found the indefinite integrals. Step 3, fundamental theorem of calculus. Usually, if my indefinite integral had a constant, I just put that constant out front and said arctangent of the upper limit minus arctangent of the lower limit. Same thing with the second limit.
Would it be minus arctangent A?
Yes, I said lower limit, and then I wrote 0 instead of A. Thank you.
I thought the first one would be arctangent B.
No, it's always about the fundamental theorem of calculus is f of b minus f of a. Upper limit minus lower limit. Arctangent b minus arctangent 0. Can you see why in this step, can you see why it really didn't matter what we used as a breaking point? We decided to split our integral at 0, but even if we had decided to split our integral at 2, we'd have a positive 3 arctangent of wherever we split, and then a negative 1 right there. That would cancel each other out. That's why that breaking point doesn't matter. All arctangent 0, 0, and what is, that's 0, what is the limit as a goes to negative infinity of arctangent A? Where does arctangent go as its argument going to negative infinity, forever to the left? Yeah, that's a horizontal asymptote on arctangent. As x goes forever to the left, your y's are going to negative pi over 2. So that's 0 minus negative pi over 2. And then what's arctangent of b as b goes to infinity?
Can't forget your 3.
Can't forget my 3. You're right. I can't forget my 3. What is arctangent of b as b goes to infinity? Yeah, positive pi over 2 minus 0. So this is 3/2 pi. That's 3/2 pi. And what's 3/2 pi plus 3/2 pi? Here. That integral converges. And the area of under the curve 3 over x squared plus 1 from forever to the left to forever to the right, that area is 3 pi. Exactly. Not approximately, but exactly. All right. We're not going to have time to get all my examples done, but let me show you what we're going to do with improper integrals. We've already done improper integrals that were improper because it had infinity or negative infinity as one of the integration limits. But what about when it's improper for the other reason? The other reason was it had infinite discontinuities, a finite number of infinite discontinuities. Let's just call them x vertical asymptotes. When we have a vertical asymptote at the left endpoint, we're gonna rewrite the integral. We can't integrate from a vertical asymptote to b, but we can integrate from, oh, this one was the vertical asymptote at b. Yeah, this was the vertical asymptote at b. We can integrate from a to some number c as c goes to b from the left. If we have a vertical asymptote at the left endpoint, even though we can't evaluate an indefinite integral on that vertical asymptote, we can approach it from the, wait. Oh, I have looked the wrong hand. This is B. This is A. This is B. B is the right endpoint. We can, or B is the upper limit of the integral. We can approach B from the left. And when our vertical asymptote is at A, that's why A is not included there, we can't evaluate the definite integral on the asymptote, but we can say our lower limit is approaching that asymptote from the right. And then if we have an asymptote somewhere in the middle, we're going to have to split our definite integral into two definite integrals. And then these two will be analogous to those two. All right. Same 4 steps though. Rewrite using the definition, using the limit definition of improper integral, and then find the antiderivative, evaluating using the fundamental theorem of calculus, and then take the limit. So what about this one? Where does that have a vertical asymptote? At 0, which is the left endpoint. That means we can't leave 0 as our lower limit of integration. We're going to have to say the limit as that lower limit approaches 0. We'll call that lower limit A. A approaches 0 from which side? If our vertical asymptote's on the left-hand side of the integral, we can approach it from the right. So we're finding the limit as A approaches 0 from the right of the integral from A to E of natural log of x squared dx. And whatever it takes to find that definite integral. I have learned, after many integration problems, that anytime I have natural log of something to an exponent, makes the integration easier if I bring the exponent out front. First, I bring it out in front of the natural log, but really that means I can bring it out in front of the integral sign. What does it take to integrate that? Do I know that the antiderivative of natural log of x? It takes 5 parts. Either that or a formula. And I'm not going to give you a formula if there's some other way you know how to integrate it. But the way that we have integrated natural log of x in the past is by parts where we let u be what? Yeah, that's the L in our acronym. The logarithmic portion is u, and then du is 1 over x dx. That means v is only the dx, excuse me, dv is only the dx, and that means v is just what? If dv is dx, then v is just x. So, don't lose my limit notation. Limit as a goes to 0 from the right. And then my integration by parts begins UV, x natural log of x.
Would you put the 2 out front instead?
Yes, thank you. Keep an eye on me. Still got that 2 out front. UV minus the integral from a to e of v du. What's v du? Just dx. What's the indefinite integral of dx? Just x. And I need to evaluate that from a to e. So limit as a goes to 0 from the right. Don't forget my 2. Put e in place of both of the x, or all 3 of the x's. That's a pretty funny expression. Minus, put a in place of all 3 x's. I think I could sing that. It looks like yodeling or something. What's e natural log of e minus e?
0.
That's great. That's just 0. So I've got the limit as a goes to 0 from the right of 2 times 0 minus a bunch of stuff with a's in it. Hey, I distributed that negative just because I didn't want to keep up with the parentheses anymore. What's the limit of that as a goes to 0 from the right? As a goes to 0. Think of the graph of natural log. Where is it going as a gets closer and closer to 0 from the right? It goes to negative infinity.
So you're multiplying that by 0, aren't
Yeah, which is a problem
you? Yeah.
because 0 times infinity is indeterminate. And that reminds me, Sam, of something I wanted. As soon as class was over Friday, I realized that you said something and I agreed with it and it was wrong. You might have been joking, which just makes me wrong. But we evaluated some limit, came up with some indeterminate form. I don't remember what it was, something like 1 to the infinity. And then we did the whole problem and it turned out to be e. I don't know what the real numbers were, but you made a comment such as, so 1 to the infinity is just e. You realize what's wrong with that statement? It's not always e, or 1 to the infinity wouldn't be indeterminate form. 1 to the infinity was e on that problem. But the whole reason 1 to the infinity is indeterminate is on some other problem, 1 to the infinity could have been something else. So I'm glad I didn't say that. All right, so, gosh darn it, we can't do this. Can't take the limit in that form. It's not one of the forms that we can use L'Hopital's rule on. Can you think of how we could rewrite it? To get something that we could use L'Hopital's rule on? There was a trick that came in handy several times on last night's homework. Let me put in a middle step and see if that rings a bell. Let's see. All right. Did that ring any bells? That was our trick that came in handy a lot of times in working with L'Hopital's rule. We could write A in the numerator as 1 over A in the denominator. And I lost my 2 again, but I'm looking out for it. The reason that that turned out to be a very handy tool to have with L'Hopital's rule is when we took, well, by direct substitution now, we would have infinity over, it goes to 0. We'd have negative infinity over negative infinity now. That's why we can use L'Hopital's rule on that and say the derivative of the numerator would just be 1 over A, and the derivative of the denominator would be what? Mm-hmm.
It would be negative, would it?
Yeah, wait. No, actually it wouldn't. It was negative here, so when we took the derivative, it would be positive. Thank you. What does all that clean up to be? That's just A. So what's the limit as A goes to 0? 0. Miles' law of calculus. All right, I wanted to do 2 more, and we don't, oh, actually 3 more, and we don't have time to. Let me just show you one thing. The reason I wanted to do the second one is because the vertical asymptote's at the right endpoint. The reason I wanted to do the third one is the vertical asymptote's in the middle. That just means we have to break it into 2. And then the most fun, second most fun of the day, doubly improper integrals. Doubly improper integrals have both infinity as one of the limits and the vertical asymptote somewhere. It really didn't turn out to be harder. All right, sounds worse, but it really didn't turn out to be harder. Since the vertical asymptote was at the lower limit, we had to do the limit as A approaches 1 from the right. And since the upper limit was infinity, we had to go limit as B goes to infinity. And then, very last thing I want to show you. Just when you think calculus can't get any more fun, there's Gabriel's horn. Gabriel's horn. I'll let you look at that example in the book. But it has a finite volume and an infinite surface area. How the hell can something with infinite surface area have finite volume? Only in theory. All right, that's it. I want you for homework to tackle that 17 through 47 that I have at the bottom of the handout. Finite volume, infinite surface area.
That's good job.
Yeah, I think it has something to do with a black hole. I don't know. Mackenzie.
This was the good last lesson of counting.
Today is the last day that you can drive.
I'll go now.
If you're here
That was
tomorrow,
fantastic.
you've reached the point of no return.
Well.
I do not want to only have 2 students in this class tomorrow.
Back every day.
Maybe.